This podcast is covering the topic 11.1c of bonding and intermolecular forces. You see by the pictures below that we have a good deal of forces to talk about. We will talk about bonding, ionic, covalent, metallic. We'll talk about what happens when these atoms that make up molecules line up. We'll also talk about forces between molecules. So let's see the assessment criteria. The assessment criteria for this topic is as follows. We'll understand how ionic bonds are created and describe observed features of ionic compounds. We'll look at the structure of crystal lattices. We'll look at metallic bonds and metallic properties. We'll look at covalent bonds and subsequent bond polarity. We'll make sure you know how to use point and crosses diagrams in order to show the formation of covalent compounds. And we'll also look at three kinds of intermolecular forces: dipole-dipole, van der Waals or London forces, and hydrogen bonding. The first thing we need to do is to look at ionic bonding. Ionic bonding is nothing more than a transfer of an electron from one element to another to form a more stable compound. Look to your left at the picture of sodium and chlorine. The outermost electron in the sodium takes up the remaining electron place in the p orbitals. So the electron that sodium had spends now the majority of its time with chlor. Now, we often see these happen with elements that have low electronegativity versus an element that has high electronegativity. Or similarly, an atom that has low ionization energy and one that has high ionization energy. Now, we show this in shell structure form, but sodium and chlor are still involved in an unequal sharing. Sodium has given up its electron, but it still remains sodium. But now it's a sodium ion. Now, in ionic compounds, we find them oftentimes to be hard and rigid because oftentimes in the solid phase, they are in a crystal lattice. You'll see some crystal lattices on the right. What you should notice about these crystal lattices is no matter where the minus charge is, there is never a plus charge immediately next to it. So the positive and the negatively charged ions remain close to their respective original elemental form. Covalent bonding is an equal or almost equal sharing of electrons between two elements. For example, two oxygen molecules can bond together and make an O2 molecule. That's an equal sharing. Now, if there's an unequal sharing, it depends upon the size of that unequal sharing to give an indication of the bonding. If there is unequal sharing that does not result in an ionic bond, most oftentimes you will see a polar covalent bond. Polar means somewhere there is a plus side of a molecule and a minus side of a molecule, where electrons might spend more of their time by, but not completely, as you would see in ionic bonding. Metallic bonding is a sharing of electrons between many atoms of one element. It's often described as a positive ion surrounded by a swarm or a sea of electrons. This sea of electrons helps give metals some of their properties, like conductivity, the transfer of electricity across metal atoms. Bond polarity depends upon electronegativity. If you look at the examples to the right, chlor both have the same electronegativity, so they have a nonpolar covalent bond. H-chlor has a polar covalent bond because the difference is not so great between the two electronegativities that would make it into an ionic bond. The greater the difference between electronegativities, the greater the dipole moment. You can see how the dipole moment can be shown numerically by looking at the bond dipole arrows. Sometimes arrows are used, as you see there, but most oftentimes we use a sigma with a plus or a minus sign. Now, the consequences of bond polarity allow for attraction between molecules of the same or molecules of two different kinds. Another consequence of bond polarity is the creation of places in a molecule where another element might attack. You can see that C with a plus sign next to it. It might be available for attack by a minus charged atom, ion, or element. This is just an example of how we use dots and crosses, or points and crosses, to show formation of bonding, primarily used for covalent compounds. Here is the intermolecular forces that go on: dipole-dipole, van der Waals, and hydrogen bonding. Because we have different charges or different poles on one molecule, the negative polarity of one molecule might attract the positive polarity of another molecule. Here you see H-chlor molecules where the OH and the chlor are attracted to each other, and it's called dipole-dipole interaction. Now, if in fact the dipoles are constantly changing and you can't tell where the dipole is, you have what's called an instantaneous dipoles. But these dipoles act just like a dipole-dipole interaction, but they exist for much shorter periods of time. These are called van der Waals or London forces. The third and last kind of intermolecular force is hydrogen bonding. And hydrogen bonding is where we have a hydrogen atom that is attracted to an electronegative atom of a different molecule. Because oxygen has a lot of electrons, hydrogen is somewhat attracted to that oxygen, not to the level of breaking its current bond with its other oxygen, but in enough of a relationship to affect boiling point, to affect other physical properties. The following video will take these 7 topics and talk about them one more time to help you get a feel for the kinds of intermolecular and intramolecular forces.
7 types of bonding. Let's see if we can do this without too much frustration. Kicking off with ionic bonding. Well, those are ions up there, positive and negative ions. Normally the metals are positive, and non-metals are negative. Strong sort of bond. There was that tough guy right in there. And you can see it, they're arranged in a neat, regular pattern. That's called a lattice. Now, people mistakenly think that ionic bonds are unidirectional, but they are not. So that model there is wrong with those 2 I'm playing with. They are omnidirectional. The bond goes in all directions. And like I said, it's very strong. It's hard to pull individual ions out of the lattice. In fact, I'm getting a little bit frustrated. Okay, on to covalent bonding. Another intramolecular bond within the molecule. It's strong, like tough guys. Oh, who's that in there? Dr. Atkinson. There he is. So covalent bonds, co means together, valent means valence electrons. So you've got to put the valence electrons together. Let's pretend these are 2 hydrogen atoms. That's the orbiting electron and the central proton in the middle. Now, if I bring those together, then I can... if I bring those atoms together, then the electrons are going to want to pair up and be shared in the middle. Now each atom thinks it has a full outer shell, and you've just made an H2 molecule, a hydrogen molecule. The outer shell almost always is full in this situation. The third intramolecular force is metallic bonding. That is positive metal ions in a sea of electrons. Let's go into the sea. Sometimes it's ordered, sometimes it isn't. It's a strong sort of bond because there's that tough guy again. But he's a robot, he's metallic. And he seems to be adding another sort of atom that would make an alloy. Alright, now we're on to the 4 sorts of intermolecular forces between one molecule and another. So van der Waals is now the name for these 4 sorts of forces. Start with hydrogen bonding. That's not quite as tough as the other bonding, not quite as strong. Weaker is dipole-dipole. Weaker still, dipole-induced dipole. And the weakest you need to know are these London dispersion forces. That is the weakest of all the bonds. And they are intermolecular between one molecule and another. Oh dear. We'll get back to that. F, O and N. If hydrogen is bonded to an F, O or an N, you're going to get hydrogen bonds. Typhoon, rain, is fond. That kid's playing too. So that's how I remember it. Fond is rain and Thai. F, O and N. They're the most electronegative atoms that are small. So fluorine loves electron pairs in a bond. Fluorine loves the electron pair bond. Okay, so now they're going to have dipoles. These molecules, the electrons are not spread out evenly. The fluorine end is going to be a little more negative, and the hydrogen end is going to be a little more positive. So you can show it using this arrow. This is really clumsy. Oh, it's not going to fit. Right, chuck that. get rid of that. Doesn't work. Ooh, almost got that guy there. So now the slightly negative fluorine is going to attract the slightly positive hydrogen in the other molecule. And that's called a hydrogen bond. There's a chicken there. Arabic for rain is shitta, by the way. Chlorine's going to pull the electrons in the bond over because it has a higher electronegativity than hydrogen. And this is pretty much the same, except this is called a dipole-dipole attraction. It's only a hydrogen bond attraction if it's with fluorine, oxygen, and nitrogen.
The following questions are here to start your thinking. Again, if you need to retake a formative, you must answer these questions, turn them into the teacher before you take another formative test.